So last time we had stated the thinning result and said we'll prove it today. So that's what we are going to do today. So let's quickly recall the thinning result. Suppose you have a homogeneous Poisson process NT with rate alpha. You take a sequence of indicators I1, I2, etc., which are IID Bernoulli P, and this entire sequence IJs is independent of the process NT, which basically means you take finitely many of NTs and if you finitely many of these IJs, those two random vectors are going to be independent for every finite choices from these two processes. Then the thin process N bar T, which is defined as the sum of all IJs as J runs from 1 to NT. This as a process is again a homogeneous Poisson process and its rate is P alpha. We also discussed what this N bar T means. Basically means that you have the homogeneous Poisson process and you have the arrivals. Now, each arrival survives with probability P independent of each other and also independent of the entire process of arrivals. Then the process of survived arrivals, okay, is again a homogeneous Poisson process, and that has rate P alpha. That's precisely the statement of this theorem. Now we would like to prove this theorem. And how do we prove it? Of course, we know that we have a characterization result of Poisson process, which tells us that in order to prove that a process is homogeneous Poisson process with certain rate, we just have to show three things. One, the first is that it has independent increments. Secondly, we have to show that it has stationary and Poissonian increments with the appropriate Poisson parameter, okay, of the increments, and we have to show that it starts at 0. So once we show these three things, which I am denoting by 1 bar, 2 bar, and 3 bar, because these are statements about the N bar process. Okay, once we show 1 bar, 2 bar, and 3 bar, we are done. Okay, so among these three things, the easiest would be to show 3 bar. So that's because N bar 0 is just J equal to 1 to N0 of Ij, but N0 is 0. We know that N0 is 0 with probability 1. Therefore, you are always summing from 1 to 0 with probability 1, and therefore this is 0 with probability 1. So 3 bar is the easiest of all. We have to actually show 1 bar and 2 bar. The way we are going to proceed is that we will actually show 2 bar in full details and then only sketch the proof of 1 bar and leave it for you to fill up the details. So let's start with recalling the hen and egg problem, because we are going to need it in the proof of 1 bar. In the proof of 2 bar, actually. Okay. So the problem was, suppose the number of eggs given by a hen in a specific year follows a Poisson distribution with parameter lambda. This had nothing to do with Poisson process, it's just about Poisson random variables. Assume that each egg hatches with probability P independently of each other and also independently of the total number of eggs. Then what is the distribution of the number of baby chicks in that year? So we formulated this as, so for each J, we defined an indicator random variable Ij that denotes the indicator that the jth egg hatches. Then of course, by the given condition, the sequence of IJs is a sequence of IID random variables with that follows Bernoulli distribution with parameter P. And also, let n be the total number of eggs given by the hen in that year. Then again, by the given condition, n follows Poisson lambda, and also n is independent of this Ij process completely. The number of baby chicks in that year is n bar, which we have seen is just the random sum of ij's from j from 1 to n. So this is the idea is the same. Each egg is think of them as an arrival, and then it survives with probability p. So this ij gives you the indicator that it survives. By survival, here it means it hatches, okay? And then therefore the total number of survival, which means total number of baby chicks born, is just n bar, which is this random sum. Now we know that conditionally on n, for any n, for any non-negative integer n, conditionally on capital N, taking the value small n, n bar follows a binomial distribution with parameters n comma p. Okay, this is true also with the convention that binomial 0p just denotes the value 0, the random variable 0 with probability 1. Okay, so if it's when n is 0, which we just mean by binomial 0p, the random variable 0. Then using probability generating functions, we showed that unconditionally this n bar is Poisson with parameter p times lambda. Okay. We are going to use this result in the proof of 2 bar. So let's try to show 2 bar. It's going to be a long proof, so let's first try to understand what we need to do. Okay. So we need to take s less than t, s being non-negative. We have to show that nt minus ns has same distribution as, n bar t minus n bar s has same distribution as n bar of t minus s. And n bar of t minus s follows Poisson with parameter p alpha times t minus s. Okay, this is what we have to show. Now note that I1, I2, etc. IID following Bernoulli P, this is given to us in the theorem. And n of t minus s, since the n process is a homogeneous Poisson process with rate alpha, so n of t minus s is just Poisson with parameter alpha times t minus s. Not only that, since the entire process is independent of the sequence ij, in particular n of t minus s is also independent of ij's. So we are in the setup of the hen and egg problem. Therefore, by using the hen and egg problem, it follows that n bar of t minus s, which is this random sum, j equal to 1 to n of t minus s of ij, this has to follow Poisson with parameter p times lambda, where lambda is this guy, alpha times t minus s. Therefore, n bar of t minus s follows Poisson with parameter p times alpha into t minus s. This is just a consequence of the hen and egg problem. So therefore, we are left to show this equality of distribution. So we need to show that n bar t minus n bar s has same distribution as n bar of t minus s. That is to show what is n bar t. Recall that n bar t is the sum of ij's, j running from 1 to nt. Similarly, n bar s is the same thing, where instead of running the sum all the way up to nt, it's enough to run the sum up to ns. Okay, so we have just written longhand what is n bar t and what is n bar s. Similarly, on the right hand side, we have written longhand what is n bar of t minus s. Okay, so we have to show this equality, which is same as showing. So right hand side we keep the same. In the left hand side, we just observe that ns, of course, is less than or equal to nt, because s is less than t. So with probability 1, ns is less than or equal to nt. And therefore, this is just the sum of ij's running for ns plus 1 to nt. So we just have to show this equality here. So what we will do is we are going to spend time on this and show this in details.